Yeah, hi everyone. Good afternoon, good morning, and good evening to all those who joined us from across the world. We'll just give it for another couple of seconds so that we don't want any of you to miss out on the insightful session that we have from our experts today. So just give it another 10 seconds, everyone, and then or 10, 15 seconds, and then we'll soon start the session. Yeah, I see we have a lot of people joining in, and I don't want anybody of you to miss the session today from our experts. Great. Yeah, once again, hi all. I don't want to keep any of you waiting who's already joined. Also, once again, good morning, good afternoon, and good evening to all those who joined us. I'm Anish Krishnan, Head of Marketing at 𝐭𝐤𝐥𝐥 Group, and I welcome you all to today's session on why engineering decisions still fail to show up in operations, what enterprise leaders must rethink in 2026. Once again, we would like to thank you all for joining us. Design intent often degrades as it moves from engineering systems into enterprise workflows and ultimately into operations. And in 2026, the gap between engineering decisions and operational outcomes has become a strategic risk. Today's research-led sessions from our experts unpack where the breakdown occurs between engineering technology, information technology, and operation technology, why adding more tools does not solve the problem, and what engineering leaders must rethink to ensure that design intent consistently drives predictable operational performance. I'm pleased to welcome Narayan Gokhale, Vice President and Principal Analyst, Research and User Consulting at 𝐭𝐤𝐥 Group, whose deep expertise spans manufacturing, industrial systems, and the convergence of IT, OT, and ET. Joining him is Anuj Mani, Principal Analyst from Operation Technology Software, who brings along strong insights into process automation, AI, analytics, and digitization across industrial environments. Together, they will provide a real-world perspective on how engineering to operational gaps emerge and what leaders must change in 2026 to close them. We encourage all of you to raise your questions in the Q&A section below. And towards the end of the session, we'll be addressing all your questions. With that, let's get started and over to you, Narayan.
Thank you, Anish. Thank you for that introduction. And I hope my voice is audible to everyone. I and Anuj, we will try and make it as interactive and as conversational as possible, to kind of drive across the points that we want to make. So Anish, if you could kind of go to the next slide. The way in which we want to start this particular webinar is to just to give you an idea about the research that we do in connected operations and engineering space, and why we are talking the subject that we are talking today. So we've been doing a lot of research, talking to a lot of end users, enterprise buyers, and we often hear from them about industrial decision making and why execution demands IT, OT, and engineering convergence. You must have probably thought like, why are we not considering topics like industrial autonomous operations, generative AI, or agentic AI, agent workforce, and so on and so forth, which is right now talk of the town. But since we have been researching this particular topic, we still, whenever we talk to the end users, the actual persona who are responsible for engineering and operations within manufacturing or infrastructure, we always get a feeling that, till there is a good IT, OT, and ET convergence. By ET, I mean the engineering technology. I think whatever digital technologies you are trying to build on top of it may not, yield the results that you're wanting. So we are sticking to basics because this is what we hear from the end users based on the digital maturity that they have. And therefore, throughout 2026, we will be kind of talking to you on these particular subjects. Because what we have learned with all those interactions is that industrial enterprises really do not lack, data, insights, or even design capabilities. What they lack is, the decisions across silos. Just take OT software now. OT software can deliver you visibility, but decisions can still stall. Same with IT, IoT, and edge, which is supposed to be the connectivity layer, the real-time, data where it is generated. But still, that real-time execution can break when you try to scale up. Same with engineering technology. The intent is there, but the impact gets lost somewhere in the operations. So we've been kind of hearing this story time and again. So that's the reason we thought we'll stick to these basics throughout then. And all these three themes then ladder into one narrative. As I said, we were talking to a lot of people. Like if you take the OT software piece, like why data doesn't translate into action, if you're talking looking at IoT and edge, why data doesn't execute in real time, and then if you're talking about ET or the engineering technology, then why design doesn't show up in operations. So we kind of deal with all these questions with our enterprise buyers, enterprise users, and so there are not separate issues. They are all intertwined, and they all point to same root cause, and that is that execution only works when IT, OT, and ET work as one entity, or they are converged. And that is why our 2022-2026 focus is about industrial decision making and execution. And we are not going to concentrate only on tools or software platforms or vendors in terms of how decision is getting. I just wanted to kind of lay out this context as to build up to the subject that we're doing. If we move to the next slide, so the way in which we are going to approach this year is in all these three topics, we will be conducting webinars. This is the first of this series, and it will be followed by panel discussions of experts who actually worked in industry, have faced these problems, and how are they going to resolve it. So that is the first piece. In a few weeks and next months, you will see it for the OT software and IoT and edge also. Now, considering the engineering technology itself, the people that we often interact, talk to, and research are mainly the engineering leaders in those industries, such as VP engineering, chief engineers, and head of engineering. So whatever we are going to present is mainly based on the insights that we have gathered, from these particular persona that we interact as a part of our daily research. Okay, moving on. And next slide. Okay, so some things I just wanted to make it clear. So we are going to kind of make it this particular thing very simple. So we are going to start with what is the state of discrete manufacturing investment versus reality. Now, this particular session, we are going to focus only on discrete manufacturing because discrete manufacturing, the manufactured parts have a long life cycle. They tend to last longer if you compare to the batch processes like cosmetics, food and beverage, where the life cycles, the span is relatively less. So here we are talking about aerospace and defense, automotive, med tech, industrial equipment, where the life cycle is into many years, and their life cycle is also increased. So the dynamics are totally different. For this particular webinar, it's mainly the discrete manufacturing that we'll be kind of talking with. Now, the state of manufacturing as we'll present, it looks very good on paper. The most organizations look like they're digitally mature. If you look at the architecture diagrams or the stack that they present, they also look pretty impressive. But when you go to the actual shop floor or the operations, the picture is totally different. And we'll try and get insights into that. And then we go on to the engineering to operations. What is that reality gap? Because still governance exists, there are workflows, and they are quite structured in nature. But synchronization suffers moment people step in. There are people dependencies that tend to kind of creep in. Then we'll go deeper. This is the crux of this particular webinar, like where the engineering decisions break as they move into operations, into the next stages of the life cycle. So where do they break? Not at approval, not even at documentation, but synchronization. Okay, so we will examine the synchronization, in more details as we move along. So what really causes this, structural failures or fracture points, if you may call? There are about 4 which you will find listed here. Uh, the fracture of happens between, say, engineering and operations, then between as design and as built prototypes and their production behavior, during engineering change management, and most importantly across the data silos that may exist between ET and OT. Then we will see the structural causes behind these execution gaps. Uh, like for example, what is the integration fragility? Is it really fragile? Then what are the data models? Is it different in ET? Is it different in OT? What is it? What is the governance between ET and OT? Are there any gaps there? And most importantly, the adoption culture, because implementation is not equal to adoption. So what is the friction there? Are there any shadow processes that are creeping in? And then we come to the most important point, and what is the cost? Because it's not only the direct cost in dollars or rupees, or those kind of metrics, but it has to do with the erosion that happens in the execution phase in terms of scrap, in terms of rework, in terms of delays. So those are very costly, in the long term for the organization, and the risks are pretty high. Then towards the end, we'll talk about that given this scenario, what leaders must rethink in 2026. Because digital presence is one thing, and but it's no longer a benchmark. But certainty in operations is something which is going to be really, really important. And as I kind of laid in the context, the way in which we have structured these webinars is we'll be kind of throwing more of issues and problems. There are some quantified metrics as to what happens when engineering decisions don't move properly into operations. And those costs also we have quantified. And in just to illustrate a case that if those are addressed, what could be the real benefits and ROI. But we want those benefits and ROI to be talked about and discussed in detail by our experts, by our panels who are actually working in engineering and operations to kind of drive, and that is what we would be doing in the next few weeks as a part of this. So we are laying ground for that, where our experts will actually kind of walk you as to what is the cost of what is the cost that companies have to pay when the engineering decisions don't move properly into the next stages of life cycle. Okay, I think so far so good. Let's move on to the next slide. Okay, so this is what I was talking about, the discrete manufacturing in particularly. So the digital maturity is different. We just picked up a decent level of digital maturity at organizations, because at one end, of course, you still have Excel sheets and very primitive, kind of digital maturity, where other organizations are quite good in their digital transformation journey. But still, if you look over the past decade, I think there has been a great progress, and enterprises have invested heavily in modernizing the tech stack. Now, what does that tech stack typically comprise of? Basically PLMs and its modernization, then model-based engineering with all its metadata related to product manufacturing information, so on and so forth. Then you have to look out at the industrial IoT rollouts, the MES platforms, and most importantly, the digital continuity or digital thread. So when you present this, it all looks very impressive, to the board and to your stakeholders. But because what is being propagated there is a single source of truth. I have not only drawings but 3D models. Then my shop floors are connected through IoT platforms and MESs. I have a data continuity that is architected, and it really sounds mature. But now let's move into the next, the right hand side of the slide, and then most of the times you see a different picture. Like when you ask, all this persona that I said, like a chief of engineering, a maintenance manager, or a VP of engineering, and you'll be surprised you get different answers. Just if you just ask, like, what is the configuration of the MBOM? What is the configuration of the work order that is getting executed? What is the recent revision out of that? Some simple basic questions like this, you'd be surprised that you will get very surprising answers, like which configuration is actually it is running now. Engineering says the change was approved. Of course, it has to be the latest one. But the operations say, oh, but we are running the old setup and we were planning it to do the next day, the next week. So we are not updated there. Procurement is only whatever exists in their ERP or their procurement systems. And so we have placed order based on whatever records were then in our system. And then quality says, well, something drifted in the specs and therefore there are quality issues. So if you notice, what is coming out of it, did engineering fail? Not really. No one actually failed, but because engineering followed the process, then operations said, oh, we have adopted as fast as we could. Procurement said, we are trusting the data that is on the system. And quality said, we are just telling you what the deviations are there in the product. So the alignment itself got fractured. And that's the central tension that we have mentioning here, that no one really failed. Engineering decisions were approved, they were documented, but they were not showing in operations. So that gap between digital approval and physical execution is what we are going to unpack today. And in order to make it more conversational, I'll just ask Anuj to kind of walk you through the next slide, and then I'll jump in for the next one. Over to you, Anuj, because he's the one who actually researches this on a much deeper level than me. Anuj?
Yes, thanks, Narayan. Hello, everyone. So, that gives us a very good picture of where this manufacturing stands today. What Narayan has explained us, this is going to give us very good picture of manufacturing environment today. So, building on that, I want to focus on something what I'm seeing consistently across this discrete organization is in this 2026. So, it's what I call the engineering to operation reality gap. So most of the engineering teams today, I believe they are not struggling with the governance, because as you can see, they have these modern PLM platforms with them. Their CAD is integrated. Their ECO workflows, they are very structured. Their revision controls, they are very disciplined. Also, the compliance documentation that we talk about, that is also embedded in the process. And if you talk about the engineering side, the designs are very, very virgin. They're virgin properly. The changes, they go through the formal review. You'll have the formal change impact analysis as well at your dashboards, and the life cycle states, they are very clearly defined. So if you look at this engineering side, engineering maturity side, it looks very strong on the paper. And that's why when we ask leaderships, when the leadership tells us that, they'll always say this one thing, that we have this modernized engineering stack with us. But we feel, yes, they are right in these terms. And that's and here, that's the important thing that we have observed. Like, this gap that we are talking about, it does not sit inside the engineering. This gap shows after the release. For example, an engineer who completes a change is going to update the EBOM, and he clicks the release in PLM. So from the engineering perspective, his job is done, right? But what happens next is when these things become less clean. So once this change is released, whatever happens downstream, that is really going to get really chaotic. So there are a lot of questions. For example, does this procurement automatically move to the updated structure, or someone has to double check every time that what version they are buying from? Does this MBOM reflect the changes immediately, or it requires interpretation or manual alignment every time? Also, when this all reaches to MES, the routing adjusts on its own, or somebody has to intervene behind the scenes every turn. So in this case, if you take the case of multi-plant environment, the main issue is that if all the sites are truly running, they have to gauge that all the sites, whether they are truly running on the same revisions or not at the same time, or they are just assuming that they are running on the same revisions. So in many organizations, there's still an informal coordination layer sitting on top of the system that we'll see. So you'll see someone sends a quick follow-up email just to confirm that the change has actually flowed through. You'll see a planner who is making a call to double check that routing has updated correctly or not. You'll see a supervisor walking to the plant, walking to lines, to check whether the configuration which is running on the system is actually aligning to what the system is showing or not. And sometimes you'll also notice that the small tracking sheets are flowing around the system. So this is not because the team wants the parallel processes. It's because, you know, they just don't trust this propagation, you know, from their heart. So now I want to be very, very clear here that these are not the signs of incompetence. Or they are not, you know, any governance failure signs as well. But I believe they are signs that this science shows you that your synchronization is not, you know, fully structural yet. And I believe this is where, you know, the trust deficit starts to begin. So if I want to summarize this in short, what we saw was not this, what we saw here was not a governance failure. The gap, this whole gap was actually exposed by the behavior. And that behavior tells us something very important. So if you release in PLM, you cannot expect it to translate into operational automatically. See, this shift has to happen, and it's not about adding, you know, more and more approvals every time. This is all about actually, you know, a structural synchronization. So here, your downstream systems, you know, they should not technically allow execution of, you know, outdated revisions. And most importantly, this configuration alignment, you know, it must be system enforced, and it should not be the email enforced that we discussed, you know, earlier. And once, you know, this whole synchronization is structural, you'll start seeing the behavioral changes naturally. And on the floor, you'll find, you know, the manual checking reduces, the search time drops, also your design reuse increases. And this is the state where you can see the trust has returned to the shop floor. And that is the core insight for this section, the whole gist of this section, that you can have a strong decision governance, you can have a strong design governance with you, and you'll feel, still you'll suffer from a weak execution synchronizations. Here, governance is going to control the design, but the synchronization part that we have explained earlier, it is going to control your execution. So if your synchronization is not structural, people are going to compensate. And if it's structural, the system is going to carry the discipline. I hope you got my point from all these slides. And yes, this for next slide, I would like to hand over it to Narayan.
Yeah, so Anuj, thank you for putting lights on there. But before Narayan sir, and before we go ahead with the next slide, I would just like to run a poll regarding what Anuj just mentioned. I just want to understand, where do engineering decision often or most often break in organization from the audience point of view? To all the audience, I'm just running a poll. I'm sure that it will come as a pop-up through all your windows. We encourage all your participation in this to understand your perspective on where do engineering decision most often break in your organization. To all our attendees, these webinars are conducted for you, for your understanding, to betterment of your organizations. I encourage all of you to participate in our poll so that we get a better understanding of what exactly are the problems that you're facing. Okay, I see a lot of answers coming for due to data silos. Okay, I see questions coming from during PLM to ERP. I hope our experts are taking a note of all these polls. As the poll is running behind, we are taking notes of what your pain points are. And with respect to this, we'll be coming up with new sessions. Well, yeah, thank you guys. Thank you for your participation. Over to you, Narayan sir. Narayan sir, I believe there is some audio glitch there from your end. If you could just unmute yourself.
Sorry, I'm sorry.
No problem.
So thank you very much for that poll and making it more interactive, Anish. And if you could move to the next slide. So stay here, even though it's only a one line, because I want to lay certain context, I think, till we move to the next slide. So stay on this particular slide. So what we have done is, you know, in order to get, you know, the real life insights, those insights are coming from about 4 different discrete manufacturers or whom we interact, whom we have researched and have run, a VOC, that is voice of customer resonance kind of surveys. So one is the aerospace parts manufacturer, aerospace, very, very highly complex discrete manufacturing. Then other one is mainly related to a automated test equipment manufacturer who then in turn serves automotive. Then there is a global electronics manufacturer, into semiconductor, and then there is a global industrial equipment manufacturer. So we're trying to cover insights from all these discrete industries. So before we come to those particular insights, so where does the decision break in the life cycle? So just I want to lay the context. So when we go one level deeper, we understand that engineering maturity is not really the problem. Then where do those really decisions break? That becomes quite interesting. So in our experience, they rarely fail at approval. They tend to fail in synchronization. Remember, I mentioned this earlier. It is this one particular weakest link where failure tends to happen. They fail between systems if they are siloed. And when they fail, when your digital structure and your physical behavior are not in tandem, they fail most importantly, we'll talk about in engineering change management or change propagation. So what I'm going to do is I'm going to walk you through this. And as I said, it is just not theory. It is based on structural breakpoints that we have seen in these particular 4 cases, which I just mentioned. So with this context, let's move to the next slide. Okay, this is what I was mentioning earlier, the engineering to operations synchronization gap. So I mentioned about this particular, aerospace manufacturer who's building components. Remember, aerospace is highly complicated, complex assemblies. There are thousands of parts in it. Configuration is very, very strict. Quality and compliance, again, is very, very strict. You have very, very detailed traceability requirements. So this is very typical of any aerospace scenario that you would think. So here again, what we observed is that on paper, the digital maturity really looked very good. The PLM was managing EBOM, that is the engineering BOM. ERP was handling the procurement and material planning, which is one of its core functionalities pretty well. MES, the execution layer in between, was driving the execution between shop floor and production work flows. Then you had a good engineering change management also in place. Serialized part tracking was also in place. And most importantly, as what Anuj was mentioning, revision control or version control, as it is called, that also seemed to be quite effectively defined. So, an engineering standpoint, the governance really looked very solid. But when a design update occurred, for example, a fastener, a fastener has to change because these are small parts which often keep changing. A bracket reinforcement sometimes, or a wiring harness, again, one of the most common places where change occurs, that the EBOM was updated. Engineering really did the job. They updated the EBOM and released in PLM. There was proper revision control. It was documented. But aerospace is not only about releasing the documents. The synchronization has to be across EBOM, MBOM, then the work instructions, the way in which the workers are going to assemble or manufacture those parts, the work orders that are coming in from your MES systems. Based on those changes, are the supplier parts being revised? Are the quality inspection plans being revised as per the change? And are the serial numbers then tracked for the records purposes? And that's where the failure or the break appeared in this particular aerospace parts manufacturer. Like ERP and MES, I think they were pretty well synchronized. EBOM was approved, but the MBOM transformation and routing updates in MDS did not reflect immediately. Procurement ended up placing orders which were on older revisions uh, because ERP had not fully synchronized. Uh, People were referring to older configurations. Now, imagine in aerospace, which I just mentioned, a very, very regulated, very, very, complex manufacturing. Uh, any configuration mismatch is a high risk and high cost. So, for example, a revision in a torque, that spec revision or a material change in a fastener, which I was just talking to earlier, can trigger a lot of rework. It can generate scrap and non-conformance and relating to delays and cost. So what did people do there? They compensated. Like as Anuj was mentioning earlier, planners took to some talks which are manual before releasing the work orders. My supervisors ended up double checking the configurations. Engineering teams again kept on doing sheets and phone calls. So approval by engineering did not mean synchronization. And this is where, like, if a structured synchronization doesn't happen, then there is a lot of cost to be paid. As you can see here on the right hand side, 60% slower approval cycles. So that's a big cost. Then teams spend 10x of the efforts for reconciliation efforts, and 75% of manufacturers were linked to, just as said, just to one aspect, which was BOM divergence. So let me repeat again, not bad engineering, again, not flawed design, synchronization latency. You know, even though the systems were connected, the state in which they were connected were not aligned, and connectivity was transferring data, but not synchronization. So in aerospace, configuration control is not optional. Release is just not an event. Readiness is a state. So until all these things come together through PLM, ERP, and EMS, it is going to be tough time for engineering and operations in aerospace. So one important lesson learned here was that integration cannot be linear. It has to be circular, and system ownership does not guarantee execution fidelity. So that was one of the things that we kept on hearing from this particular manufacturer. Anuj will throw light on another aspect which kind of highlights what we have been saying throughout this session.
Yes, yes. Thanks, Narayan, for explaining the first big point so well. So now let's move on to the different type of failure. So the first example that Narayan gave, it was about the synchronization across the whole system. But this one, the second one, is really different. This failure is about where engineering decisions break, and not because of data. The data is misaligned, but it breaks because in the real world, the model that we have created, it behaved very differently than it was predicted in the digital state or its design state. So if you see in the today's context, in many discrete manufacturing environments, the production readiness is validated digitally before it goes into the production. The readiness is we have a lot of tools to validate these kind of production readiness digitally. So in the design state itself, the routing logics are reviewed. Your capacity is calculated in the design state itself. Also, you'll see the line balancing is optimized in this state also. And also with the help of simulation, you'll find that flow of material is confirmed beforehand. This flow is confirmed before this actually go into the production environment. So if you see in this case from governance standpoint, everything looks very accurate, and hence we all assume safely that now we have validated the model. The production that we will see will be very stable, and we will not see any issues on the floor as well. But in reality, this does not go as per our plan. Most of the times you'll see the breaks are happening on the production side. So let me illustrate this with help of real world case scenario that we heard. So something which I heard from this is something which I heard from VP of engineering from one of the very prestigious global industrial equipment manufacturing company. So in their company, the production model was already validated digitally, and during this validation, they did not found any structural any structural validation they did not found. Also, they did not find any missing dependencies in the model. There were no routing conflicts that you identified during this whole processes. So this engineering department, they concluded that this design is production ready. Then this model was passed on to the production, and before the production start, this model was actually sent to the operation, and it made reality. So what production team was found out that the cycle time, they saw the cycle time exceeded the forecast by almost 12 to 18%. Also on the production line, it was noticed that the certain stations began overloading. So it was clear that this material was not flowing smoothly. It was cleared in the design state that material will flow smoothly, but when it met the reality, when it met the production lines, this material was not clearly flowing smoothly. Also, they saw this throughput drop below the design expectations. The design were expecting around something, and it expected this dropped below the 8 to 15% of the expectations from this design side. So what do we understand from this situation? So on paper, nothing was wrong. The BOM was correct. The routing logic, it was actually really documented really well. And the capacity, it was also calculated, and it was in the reasonable limit. So engineering has done their job. But when production started running at scale, the behavior of the system was different from what the model has predicted. Now, at first, this was very confusing for the both departments, because there was no visible mistake. No incorrect structures were seen there, as well as there was no broken logic as well there. So instead of making immediate physical changes, instead of making direct changes on the shop floor itself, they decided to step back and analyze the situation. They decided to analyze it with the help of some digital twin simulation tools. So they use these tools to recreate the production environment virtually. The idea was very simple. It was, if the structure looks correct, let's simulate in the real flow conditions and see how the system behaves under variability. So the results that they got, these results were really shocking for them, shocking for both of this department, that a minor routing choice that they created in the design state, when it passed to the reality, when it passed to the operation state, it created the congestion. It created a congestion between two stations, and the machine that was positioned for local efficiency, it reduced overall throughput when viewed across the entire line. So also the buffer size assumption that they made in the design state, they worked in the steady state condition, but as soon as this hit the production, it started collapsing, and because it started collapsing because of the variability that it made in the real world, right? And once they saw this all in the simulation, the problem was very clear to them. The problem was actually when as designed and as built are not always misaligned. They are always so they got the hint that this misalignment is not because someone made an error. So sometime, of course, they are going to diverge. And the reason being, the static models cannot predict all the time that this will happen, that these things will happen in real world environment. So this all cannot be predicted in the design state. So you will see this divergence in the state always. So simulation step that they took, this made this gap very visible to them. And once it was visible, it was very actionable to both the departments. And with that I think you have understood this concept, this failure very well with the example that I heard from the field. And with that context, I'll hand it over to Narayan to take us to the next place where these engineering decisions are tend to break. So maybe the next failure point he can explain you.
Thanks, Anuj. So first breakage point we talk about was the synchronization, and then what Anuj explained is more to do with how factory responded to physics-based simulation, digital twins. And now we come to another very important failure mode or breakage point, which is engineering change management. Now, and the ECO, which is the engineering change order, is the ultimate result of this change management process. So again, we were kind of interactions, and we're working with a global automatic test equipment manufacturer who does this very specialized test equipment mainly for automotive OEMs in turn. So and these particular assemblies that this machine tests is mainly the PCBs, the embedded controllers, control units, electromechanical systems, both for automotive and industrial use cases. And these particular products for industrial and automotive tend to have a short product life cycle. Component volatility is very high. As you know, today components become obsolete pretty fast, and therefore engineering changes have to be also done. And that's one of the things, especially if you're dealing with a lot of chips and semiconductor kind of equipment. So during one of the workshops, we asked them, the engineering director, a very simple question: what is your biggest friction in this particular life cycle? He didn't hesitate. He was very clear. He said, we were not slow at approvals, we are slow at propagation. Now, that statement was very powerful. It stayed with me. Because when we look deeper, again, as what we've been saying, from a governance perspective, everything looked good. Formal review boards, then workflows seemed to be structured. Everything was digitally signed off, compliance tracking. So that discipline existed. But here's the catch. During those discussions, during those workshops, we learned that the change object lived in the PLM, whereas its impact lived elsewhere. So requirements were managed in one system, and the PCB revisions, multiple BOM structures, they were somewhere else. Whatever approved manufacturers or suppliers were there, they were handled separately. Documentation changes were again processed independently. So even the component substitution was a result of ECO. That impact was also not fully visible to all the stakeholders. And so entire quality, supply chain, engineering, the same, everyone kind of suffered because of all this. But here's one case which I said we'll kind of touch upon, like they made changes. And as I said, we'll be talking more about them in the panel discussions when we come. But just to give you, like, if those rectifications or changes are made, then they were really able to kind of get a lot of good results. The ECO time, which had stretched beyond 90 days, they were able to bring it down to 14 days. The rejection rates had increased to 70%, that they were able to manage to get to 26%. There were other benefits such as the documentation which was lagging, that they were able to kind of bring on track. The approval processes became time, documentation improved. So all that change management thing really started to show results, and it yielded then in roughly $2 million of annual productivity gains. So this is what this engineering director was meaning when he says that when this change or this propagation becomes predictable, I think the results are here for everybody to see. So that's the key insight here, that ECO maturity is not about workflow efficiency, neither about the structural connectivity, or it's like how the life cycle elements are connected. It's when this propagation happens properly, you will see all those particular results. With this, I'll kind of ask Anuj to talk about the fourth breakpoint, which we have seen very often and we kind of documented here based on our interactions. Anuj, over to you.
Yes,
Next slide.
yes, thanks, Narayan. So let me take you to the last failure point and simplify it. And this is the highest voted failure point in our poll as well. So let me simplify it to you. I'll simplify it with the real conversation that I had with this head of engineering, multi-plant. This was a multi-plant industrial bearing manufacturing company. So we had a conversation with him. So they had this solid engineering setup. Their PLM was in place. Their process assumptions were clearly defined. In their environment, this production environment, routing logics were documented properly as well. The cycle time models were carefully calculated and validated. So from engineering standpoint, in this scenario, everything looked very structured and mature. But even after all this, he said something very interesting. Like he said that they had strong engineering system, but they don't know how to, how to get this live operational feedback into the systems. So what he meant was this, that machines were running across multiple plants, the production data was there, the maintenance logs were also there, the quality metric existed there, but the data was isolated from, the data was only residing in the OT system, and it was isolated from your ET and ID system. So what he wanted to say was engineering could not see, real plant behavior in the continuous way. And because of this, the performance gap were discovered late in this all propagation. Like this, the OE variance, it was not properly visible in the early states. This breakdown response was reactive instead of, it was always reactive instead of predictive. So engineering optimized structured, this engineering teams, they optimize the structure, but operations were managing reality in different isolation. So these both departments were managing the data in different realities. So now here's what they decided to change. Instead of adding more reports or more dashboard, they focused on unifying the visibility between this engineering and operations. They connected over 500 machines across plants. They standardized the data flow into this common layer, and the real-time performance metrics now it became accessible not just to the operation, but it was accessible to engineering teams as well. So what happened, this daily review meetings that shifted from looking backward at the report every time to looking at this live data layer and live plant behavior. And from this point, the things actually start changing for them. So they saw this OE improved from 78% to 81%. For them, this breakdown responses that we talked earlier, they become faster. These responses became faster. The operation variance, it got reduced. But for most importantly, the engineering decisions started being made with real production outputs, the real production feedback that get from the plant from the line. The engineering decisions also started impacting from this real feedback. So this is what we call a closed loop, right? So here's the key insight from this whole case, that the digital thread is not always about connecting different systems. This, what we really think is that this digital thread is it's more important. What is more important here is that that we close the loop by providing feedback and take feedback from this downstream system to upstream system always. And if this doesn't happen, you'll not see real optimizations, right? So with this, we'll close our 4 break points, and we'll move on to the more move on to the next slide, which is structural causes. And Narayan will take you to the slides. Over to you, Narayan.
Thanks, Anuj. Those four failure points were the crux of the presentation. And now let's see what is causing this execution gap. What are those structural causes? So we have seen the symptoms. Now let's look at what's really behind it. What are the causes? So the execution gaps are not random. If you see, they're architectural in nature. The first one, what we would like to call it, is more to do with the integration fragility and what we call it as one-way integration. So engineering will push the data into manufacturing or into operations, and the bomb is released, but manufacturing will also adapt accordingly. But what happens? That production behavior, like whatever they have adopted in production, that does not seem to travel upstream in a structured way. So again, the cycle time drifts or scrap increases or anything to do with your routing schedule, that feedback does not necessarily come. So if the integration is linear, then engineering pushes and manufacturing just absorbs. Whereas any systems that works in way will tend to be fragile, as we said, in integration fragility. So it, as we said, the causes which we kind of came up in our earlier discussions, that integration has to be circular. and not just linear. Design should inform execution, and execution must continuously refine design. The second most important cause, structural cause, is the structural mismatch. What we would like to call it as misaligned data models. Now, look, engineering behaves in a certain way. There are various engineering disciplines, like mechanical, electrical, so on and so forth. Then they also work as per different product structures. Also, there are design intents, the way in which a particular products have to be designed. So they work in that fashion. Whereas if you look at the manufacturing or operations, they tend to be sequential, that one thing has to be done after the next. So they operate in a sequence. So one machine, one station, one work cell, so on and so forth. Now, these two models are fundamentally different. And therefore, if they are not continuously reconciled, that impact then tends to get underestimated. So functional structure is not the same as sequence structure. That's one particular thing. And therefore, these models have to talk to each other continuously. And therefore, the deeper issue is just not tooling, just not different software. It's the structure alignment. Now, let's look at the next slide, where we are going to talk about another structural cause, which is the ET-OT governance gap. We talked about this in very simple terms. Engineering will own, for example, PLM, manufacturing or operations will own MES, IT will own the infrastructure, but where is the execution fidelity? Who is accountable? Who is making sure that actual release design is running correctly across the life cycle, across the plant? So manufacturing, when it runs, it runs on daily stand-ups, weekly reviews, but if this is not shared, then ownership becomes a problem, and accountability, if it is unclear, this synchronization, cannot be just optional. It has to be kind of enforced. And the last one is about typical people issues like resistance from workflow in terms of adoption, which we call it as adoption friction, or sometimes even adoption governance. So it is a very powerful one, as we just mentioned earlier. Rather than trusting systems, they trust people processes, like spreadsheets come back, site tracking emerge, then manual reconciliation. So we have shadow processes, shadow IT, everything coming into it, resistance to change. So this all kind of then leads to adoption friction, and so system ownership does not guarantee execution discipline. Workflow friction always creates workarounds, as we just mentioned above. So if leaders want executional certainty, governance must operate at operational cadence, the way in which, at what frequency the operations team is working, and system must fit into that particular thing. Okay, so I think we are running out of time, so we'll quickly kind of run through. Like with all these things we spoke about, decisions breaking, the structural causes, there is a cost that is being paid. And I think if Anuj can quickly take us to what is that cost of broken execution, I think then we can move forward.
Yes, thanks, Narayan. So as Narayan just explained, these execution gaps, they don't happen randomly. They usually come from structural causes. Now, the important question is this: what do these structural gaps actually cost in the business? For example, let's take rework and scrap. So in many cases, the design itself is not wrong. Engineering may have done everything correctly, but somewhere between the release and production, an older revision gets used, or the deviation is, it's not clearly propagated. Because of this, this older revisions, or this deviation not getting clearly propagated, the material is consumed, extra labor hours are spent, and after some time, someone realizes that there is some mismatch in the configuration. I mean, what's running on the floor and what is in the system is, it's not aligning. So this cost is more, this cost in the more rework and scrap to the whole organization. Now, if we look at the launch timelines, the pattern is similar. Engineering releases the design, approvals are complete, and from a PLM perspective, everything looks very clean. But when plants are not, fully aligned on the latest structure or routing updates, you'll find that the team spend, more time on verification and reconciliation. whether they should be spending more time on ramping up this production and all. So in this case, stabilization takes longer time than what it is expected in the design state. And in this state, there's no single team has failed. So if you talk about suppliers feel this as well. When specifications are not completely aligned across your PLM, ERP, and your manufacturing systems, vendors are going to pause and ask for clarifications, or sometimes they are going to proceed based on the last confirmed versions as well. So that creates extra coordination efforts, that creates extra follow-ups with the vendors and suppliers, and occasionally it is going to incur a lot of additional cost to the company. So there is also this compliance angle as well. So your audit preparation becomes more complex when this as designed and as built records they do not consistently match. So here teams needs to in this case teams needs to manually reconcile the data to show the accurate traceability to everyone. And I feel this over period of time, this managing this diversity is going to require more and more efforts, because as configuration and variant complexity increases, you will see these teams have to give more and more effort. Another area that often goes unnoticed is decision speed. So teams actually hesitate when they are not fully confident that the system is going to reflect the actual operational reality, the actual operational data. So they really hesitate with this kind of situation. So what they do is they double check before acting. That extra validation step that they are taking now, it looks small in this scenario, but it's slow, but it slows corrective actions, and it is going to reduce the responsiveness. So when you step back and look at it, none of these issues seem very critical in nature. None of these issues are very big that maybe you kind of miss them, but together, if you take them together, they are going to increase your cost, they are going to extend your timelines, and of course they are going to reduce this overall operational efficiency for sure. So with this, we have covered the cost of broken execution part. So I'll move on to our last part, what leaders must rethink in 2026. So, after everything that we have unpacked in this whole webinar, the synchronization gaps, the ECO propagation issues, this ET-OT disconnect, also the structural causes of this and business implications of them. So after all this, the one question that becomes very practical is that what must leaders rethink in this 2026? So the first area where leaders should think in 2026 is that the integration that we talk about, that integration must be treated as infrastructure. So I've seen in many organizations, integration is handled like a transformation project. They connect PLM to ERP, they connect ERP to MES, they build APIs in between, and they declare it as a success. But we need to think that integration is not the milestone. This integration, it must be designed, it must be monitored continuously, and it should be owned like a critical utility in the whole environment. So we should actually stop treating it as and a simple IT afterthought. Now the second shift where engineering leaders should focus is continuous traceability. So most companies have traceability, they all have traceability within their environment, but most of the time it is event based. A change is approved, a link is created, revision is released. But what happens after that? We also need to check that, right? We also need to check if production data flows back into the engineer automatically or not. Or does this design assumptions that we made in the design state, they update automatically if deviation data that we have got from the quality or production line, whether this or we need to keep in mind that the traceability must here we need to keep in mind that this traceability, it has to be bidirectional and continuous. In this way only your design intent is going to flow into the operation. And the third area where leaders should focus more is the architectural propagation. What I mean by this is that change propagation, it should not depend on email, phone calls, or someone remembering every time to update another systems always. What I mean is, when a new configuration approved, the system itself should make sure that the older revisions that cannot be used, and you should always work on the new revisions. So with this, now let's extend the thinking to one level further, and Narayan will help you to understand that. Over to you, Narayan.
Okay, so we're coming to end of this particular session, and as I said that these are some of the topics which we are expecting our expert panels to unpack, in more clarity with exact work that they do, and from horse's mouth, if you want to call it. So again, like what these leaders should do differently in 2026. So if you imagine, and what we have heard is, like talk to operations, their KPI says OEE. If you talk to quality, they say their KPI is about defect rates. Talk to procurement, they say their KPI is about costs and reduced costs. But execution, they don't really respect these boundaries. So until you have shared execution KPIs, it's very difficult to kind of bring a uniformity. Otherwise, it will only show up in one dashboard. For example, say in operations dashboard. So, and these kind of siloed culture, will not really help moving forward. Then we come to extended governance. Now, extended governance must extend beyond system ownership, not documentation, not system ownership. It's accountability, as we just income, and then the execution has to be owned. So ownership must move from systems to outcomes. That is the learning for extended governance. And then finally, so what is it is doing is setting a new benchmark, that earlier for many years digital maturity meant modernization, PLM upgrades, IoT deployment, digital threats. But in 2026, those cannot be the benchmarks. Operational certainty is going to be the benchmark as we move forward. And if the answer is sometimes, then again it's not there. So as long as you are able to kind of show that operational certainty, then it's going to be a big problem for the engineering leaders. So with that, since we run out of time, thank you very much. And whatever questions we have received through chat or any other things, we could get back to you. Anish, over to you.
Thank you, Narayan sir, and thank you, Manoj. It was definitely an insightful section. I'm sure our manufacturing leaders are better prepared to tackle the challenges that they have for 2026. So,
Yes.
like Narayan sir just mentioned, as we conclude today's session, I would like to once again sincerely thank you all for taking your time in joining us and in engaging in such an important discussion that we had today. As both of them mentioned, engineering excellence is no longer defined only by design quality or time to market. It is defined on how consistently decisions translate into operational performance. We hope today's insights have provided you a clarity on execution gaps and what emerges and what to be rethought in 2026. A special thank you to all our attendees. At the same time, a special mention to our experts in our panel today. Narayan and Anuj, once again, thank you for sharing your expertise and your insights on such a structured perspective on bridging engineering to operation gap. Your insights were both practical and thought-provoking, and I'm sure our audience also agree to the same. And to once again, to all our audience, if you would like to continue this conversation, our team would be happy to connect. Feel free to drop a mail directly to QKS Group. And we look forward to seeing you in our upcoming sessions. As Narayan just mentioned, we have a panel coming up. We have more webinars coming up. So stay tuned to our LinkedIn. At the same time, stay tuned to our website. Looking forward to seeing you all in our upcoming session. Have a great evening. And to some of you, have a very good day ahead. Thank you once again.
Thank you, Anish. Thank you all.
Thank you all.